Hello everyone. In this video, we will solve this problem click partition. This is a 2100 problems, rated problems. So let's read the problem. You are given two integers n and k, and there is a graph of n vertices. You have to assign each vertex an integer ai, which should be distinct, and it should be between 1 to n. And also, after assigning integers, you will add an edge between I and j if and only if this satisfies if the two nodes satisfy this. And your goal is to create a graph which can be partitioned into minimum possible number of clicks. Now, what is a click? A click is a graph in which every vertex is connected to every other vertex. So first let's explain you the problem. So let's suppose I am talking about a click of three nodes. Then in this, every node is connected to all other nodes. So this is a click. For four node, it is like every node is connected to every other node. So this is a click. Now, in this question, you are given an n, means you have to generate a graph of n vertex and the parameter k, such that the number of, and after that you have to partition that graph into multiple clicks. Let's see the first example. Second example. So in this, n equals to 4 and k equals to n equals to 5 and k equals to 4. So here you can see that value given to 1 is 3. So 3 is connected to which node? My condition is I minus j plus ai minus aj should be less than equals to k. So this is 3. Let's check whether it's connected to this or not. So this is the difference is 2, and also its the index difference is 2. So index difference is 1. So 1 plus 2, 3. So 3 is less than equals to k. So we will add an edge between 1 and 2. 1 and 3. Uh, the difference is 2. 2 plus 2, 4. So we will also add an edge between 1 and 3. And here 3 differences, 1 plus 3, 4. So add an edge between 1 and 4. And then difference is 1 plus 4, 5. So there is no edge between 1 and 4. Let's see. The difference is 4. No, we have to partition the graph into clicks, right? So here, okay, right. So now let's see for 2. 2 is connected to this node, no. This node, yes. 2 is connected to 4. So 2 is connected to 4. 2 is 2 connected to 5. Difference is 3. 3 plus, no. It is 3 connected to 4. 3 plus 1, yes. So 3 is connected to 4. Is 3 connected to 5? 1 plus 2, yes. 3 is connected to 5 also. Is 4 connected to 5? 2 plus 2, yes. 2 plus 1. So 2 is also connected to 4. So let's see. Here you can see that in this graph, if you consider node 1, 2, 3, and 4, then 1, 2, and then 3, and then 4. In this, 2 is connected to 3, and 2 is connected to 4, and 3 is connected to 4. This is a complete click in which every node is connected to every other node. So this is a partition and other node is 5. So we partition the graph into two subgraphs in which every graph is a clique. Every subgraph is a clique. So we have to do like this. So let's see how to approach this problem. So here you can see that uh, n is also small and then k is up to 2n. So let's see why k is less than equals to 2n. First of all, let's suppose we are given a node of n vertices, then uh, what is the bound on k? Like I want to make a clique of n size. So what is the bound of n? Uh, the maximum value of I minus j plus ai minus aj for two pair of nodes can be, this difference can be n minus 1 and this difference can be n minus 1. So total 2n minus 2. So if k is greater than equals to this, then we can make a clique of n, right? And let's see what is the uh, minimum value. Let's suppose uh, in a graph, the minimum value of this can be uh, n minus 1, right? No, this value will always be greater than n minus 1 because there is a node 1 comma 5 whose difference will be n minus 1, and this is a positive integer because every number is unique. So sum will be greater than n minus 1. So if k is less than equals to n minus 1, then we are sure that we can't make a clique of uh, n size, right? So no clique possible of n size, right? And if k is less than equals to n minus 2, then good. But let's check for k equals to n. What will happen for k equals to n? Will is it possible to make a clique of size n with in where k equals to n? Let's see. So uh, let's see. Let's assume that we are able to make this one. So we have to find a way to assign the value to nodes such that the edges formed is, and after the we connect the edges, the graph is connected. The graph is a clique. So we are given the node value. Let's arrange the node 1, 2, 3. Let's see for 3. How do we arrange the value so that uh, k equals to 3 will work here? So if I give the value like 3, 1, 2, then here every node is connected to every other node because the difference is here, the difference is 2. Let's give it like this: 1, 2, and then 3. So here the difference is between this and this 1 plus 2, 3. Here 2 plus 1, 3, and here 1 plus 1, 2. So this work means we are able to make for 3 we are able to make click using k equals to 3. Let's check for 4. We are doing this because we are just wanted to check if it fails on the base case, then we have to think of the some other solution, or let's suppose we do for 4. So and let's assign this value as like this 1, 2, 3, and 4. So in this case, here you can see that the difference is 2 and the sum is 2, and then here 3 plus 1, 4, and here 1 plus 3, 4. So here also work means k equals to 4 works here also. So let's assume that k equals to n works for n nodes. So how do we arrange the values? So if you run some test case or do some this type of things, then you will observe that uh, this is, let's suppose for n equals to this. So if you go here and try to assign from here 1, 2, 3, go to the middle, means if n is even, then go to n by 2 plus 1, and if n is odd, go to n by 2 plus 1 also here. Yeah, yes. So means n lower bound of n by 2 plus 1. 3 by 2, 1 plus 1, 2, right? And here 6 by 2, 3 plus 1, 4 is. So 1, 2, 3, and here try to assign from 4, 5, 6. And let's check this is the assignment. So let's and this is working here also. So let's prove whether it works or not here. So 1, 2, 3, and here let's prove for even nodes. So 1, 2, 3, 4, n, and then n plus 1, and then 2n, right? So what are we are doing? We are assigning 1 here, and n plus 2, 2 here, and here we are assigning n plus 1, right? So for I less than equals to n, we are assigning I plus n. Value assigned is I plus 1, and for I greater than n, we are assigning n minus I minus n. Here you can see that n plus 1 minus n. So we are assigning this I minus n. So I minus n. Now, let's pick two nodes, one from here and one from here. Two nodes I and j. So what is the value assigned to I plus n, and j is from greater than equals to 1, so the value will be j minus n. So what will be its difference? Mod I minus j, j minus I. Or you can consider this as uh, instead of j, write it like n plus j, where j is greater than equals to n. J is greater than equals to 1. So basically, we are starting j from here, j equals to 1, j equals to 2. So the value given to n plus j is j, right? So what is the difference here? N plus I minus j, and then mm, wait a second. So let's do this like here you can see that the difference is here. What is 1 n plus 1? So you if you compare this, then you will get n plus n. Mm, wait a second. So here you will one difference is n plus n. So you are getting 2n, which is good because we are working with 2n nodes. And it means you if you are taking node with I and I plus n, then these are good because the difference here is n, and also value assigned to this is n plus I and I. So the difference here is also n plus n is 2n. So this works here, right? For every I from this and n plus I from this works, right? Now if we compare, uh, let's suppose take 1, and we are trying to check whether 1 is connected to all the nodes here or not. So basically when we increase the value, this value n plus 1 to n plus 2, and when we increase this, then the this part means first part mod I minus j gets increased by 1, and the difference gets decreased by minus 1. So overall compensation is 0. Overall sum is 0. So 1 is connected to all, and this is true for all other nodes. And also if you check here, this will be simply because any nodes difference here you can see this up to 1 to n, the maximum that you can get is 2n, which is under the total number of nodes. So we are good to go. And also we can prove this for odd number also. So I hope you understand the solution, and let's try to code this. So basically we have to output we are given n and k, and you have to do the assign the values, and so that there is a minimum partition. So how will, let's suppose we are given k and n. If k is greater than n, k is greater than equals to n, then we know that for an n value k equals to n is sufficient, means we can generate an n size clip. So if k is greater than equals to n, then we can simply write one assign using this thing. I mean, you go to the middle and by 2 plus 1, and from here assign 1, 2, 3, 4, 5, 6, and then here continue on from here, right? But if k is less than equals to n, you know that we know that k is sufficient for only k nodes. So we will select the first k node and assign the values like this, then another k nodes, and at the last some remaining nodes. So we have to form this much minimum number of clicks. Means the number of clicks will be n by k seal of n by k, right? Because for some k we can make a maximum possible size of click required is that we can make is k only. So we are taking the maximum possible from here, and then k, and we are assigning the values, right? So let's see how we will code this. And we have to print the value assigned to each nodes and the number of clicks formed, and for each node we have to output in which click this belong, right? So let me show you the code. So what I have did is basically I have taken the minimum with k equals to minimum of n comma k, because if k is greater than n, then also k will work here. So answer will be, maximum number of clicks will be seal of n by k, which is written like this, n plus k minus 1 divided by k. And this will store the value assigned to each node. So we are going from 1 to n, and then I am taking k jumps, because I will assign L equals to I and R equals to minimum of I plus k minus 1, means I am taking a window of k length from I to I plus k minus 1. And from L to R, what I will do, I will generate the values that should be given to this range. Means let's suppose k equals to 2, and then I am taking L as 3, and so the range will be 3 to 4, and I have to give the value from 3 to 4. This does not matter because all the numbers are shifted by 2, so we can apply the same algorithm here that we have applied here. Means we will go to middle, and then I will assign 3 here and 4 here. Let's suppose k equals to 4, then 5, 6, 7, 8. So we'll go here and I will assign the minimum value of 5, then 6, then 7, then 8, right? So I am doing the same here. This generation will will assign the value from L to R. So what this does is first find the length, and then it go to the middle n by 2 plus 1, and then from mid to end it will assign the nodes like from I minus mid plus L, means L plus 1, L plus 2, something like that, and then here the last element plus 1. So it will give the value assigned. Now this is a one index, and I have to assign from L to R. So I will from I will add I to all the values. So all the index. So value of I plus j minus 1 is b1 of j, right? So this is the value, optimal value, and what will be the click? Click will be like first k indexes will be given to the first click. So count is equals to 1, and so first k vertices will receive click number one, then I will increase the count, and then this will go on, and then this will work. So here you can see that. Also, if you have any doubt, you can comment here. Like for 2, 3, the assignment is 2, 1, number of click is 1, and then both nodes belong to the same click, right? So this will work fine, right? And thank you. And if you have any doubt or anything to discuss, you can comment. Thank you.